In October 1945, the last flyable Japanese bomber remaining at the Rabaul stronghold prepared for a definitive mission. This was a Nakajima B5N2 torpedo bomber carrying the tail code 302. It belonged to the 105th Naval Base Air Unit. The objective was not combat, but the formal surrender and safe delivery of the aircraft itself. Securing the specific airframe meant taking possession of a fully intact tactical platform. The operational constraints of moving a former enemy aircraft across monitored airspace created immediate logistical friction. The crew had to execute a flawless transit to a designated airstrip, relying on strict adherence to a prearranged flight path to avoid interception. On October 14, 1945, just after 9 a.m., the Japanese pilot Goro Kataoka initiated the takeoff roll from Vunakanau Airfield. The aircraft climbed away from the volcanic terrain, carrying its crew on their final operational flight. The destination was Jacquinot Bay, located on the southern coast of New Britain, where Allied forces waited to take official custody of the machine. Escorting the bomber were 4 Royal New Zealand Air Force F4U-1 Corsairs. The escort requirement was a strict procedural mandate. Their role was procedural and unforgiving. Keep the Kate in sight and keep it on the agreed corridor. Shortly after reaching cruise altitude, a navigational deviation occurred. Kataoka drifted onto a westerly heading, steering the bomber away from the surrender point. This unexpected turn instantly raised the stakes for the escorting F4U-1 pilots. They had to correct the trajectory of an armed aircraft without escalating the situation or triggering a defensive response from the bomber crew. Without direct voice contact for real-time instructions, the Royal New Zealand Air Force pilots relied on close formation visual signaling to correct the bomber's course. In that kind of escort, correction happens by sight and position, not by voice. The intercepting fighter must close the distance and establish an extremely tight formation, matching the exact airspeed and altitude of the target. This geometry allows the intercepting pilot to establish direct line of sight with the bomber cockpit. Using highly deliberate and unambiguous hand signals, the fighter pilot dictates the required heading changes. The procedure carries severe collision risks due to the required proximity of the wingtips in turbulent air. It also risks misinterpretation. One sharp pitch or roll can look like a break for it. Escort pilot Brian Cox maneuvered his Corsair directly alongside the Kate bomber. He flew close enough to visually command Kataoka to adjust his vector, physically pointing the bomber back toward the coast of Jacquinot Bay. The visual correction succeeded without triggering an incident. Kataoka acknowledged the physical commands and carefully banked the aircraft back onto the authorized eastern route. The formation stabilized, crossed the rugged coastline, and descended toward the Allied airstrip. The bomber touched down safely, completing its final approach. Upon engine shutdown, the aircraft was formally surrendered to the military ground authorities. The aircrew disembarked and the operational flight log of Tail 302 officially closed. Following the administrative transfer, the ground crews faced an immediate spatial constraint. Jacquinot Bay was a forward strip with limited covered storage, and the captured aircraft had no secure hangar space reserved for it. The bomber was parked out of the way and left exposed to the elements. In the coastal heat and humidity, corrosion began its slow, relentless work. Rainwater, salt air, and daily temperature cycling attacking thin skins, fasteners, and linkages. The operational history was complete, but a decades-long process of material degradation had just initiated. How does an intact aluminum airframe survive decades of open-air tropical exposure without any form of protective maintenance? By the time the first salvage attempt was even possible, Tail 302 had already endured 36 unbroken years in the open at Jacquinot Bay. It wasn't protected by mud or deep cold water. It sat in air, rain, and heat, so the problem wasn't a scattered crash site, but a slow, continuous chemical breakdown. The initial site survey revealed a crucial advantage regarding the overall shape of the aircraft. The baseline geometry of the aluminum hull benefited directly from kinetic neutrality. An aircraft that lands intact rather than crashing retains its factory geometric alignment, meaning restoration focuses entirely on surface decay rather than untangling compressed structural frames. Because the bomber executed a controlled landing on the runway and simply rolled to a stop, its main fuselage structure remained geometrically straight. The absence of deceleration impact meant there were no sheared rivets from sudden stress loads and no crushed wing roots from colliding with terrain. The straight airframe baseline provided an exceptionally stable platform for any future recovery. Straight alignment didn't buy the airframe any mercy from the jungle. With the aircraft abandoned, moisture turned every mixed metal joint into a battery, a wet electrolyte linking steel bolts to thin aluminum spars. A microscopic current flowed, and the weaker metal sacrificed itself first, pitting skins, loosening fasteners, and freezing linkages in place. Over 3.5 decades, and that galvanic cycle quietly thinned the Kate's outer panels long before anyone tried to move it. By 1981, the wreck had already been partially disassembled and moved from the airfield area, its condition worsening with each passing season. In the mid-1980s, aviation specialist Brian Bennett arranged for the engine to be removed and transported for preservation, recognizing that the densest cluster of precision parts was freezing into corrosion. Bennett executed a focused salvage effort to separate the Sakai series engine from what remained of the airframe. This power plant, commonly identified as a Nakajima Sakai 11, was rated at about 1,000 horsepower at takeoff, a dense and highly complex mechanical assembly. Extracting it required overcoming decades of rust. But Bennett had to sever the heavily corroded engine mounts at the firewall and manually disconnect the seized control linkages, fuel lines, and electrical harnesses. Dropping the heavy steel mass away from the lighter aluminum fuselage broke the localized galvanic circuit. This separation reduced one of the worst steel on aluminum interfaces at the forward bulkhead, helping slow further corrosion at that joint. The extraction required careful handling to prevent the heavy engine from collapsing onto the remaining airframe or sinking further into the soft earth. Once freed from the airframe, Bennett transported the power plant away from the uncontrolled jungle environment. He subsequently donated the engine to the Kakapo War Museum. Moving the engine indoors successfully isolated the complex machinery from the daily cycles of heat and moisture. It was a partial but highly effective preservation step. The power plant was saved, but the vast majority of the airframe was left behind at the landing ground. With the engine removed, what happens to an unmonitored shell left entirely accessible to local populations? By the year 2003, an assessment team arrived at the jungle boundary to evaluate the surviving structure. The site presented a severe evidence contradiction. The aircraft had executed a controlled, wheels-down landing decades earlier, perfectly preserving its primary fuselage geometry. Yet, upon closer inspection, massive structural assemblies and heavy mechanical components were entirely missing from the airframe. This condition was the direct result of component scavenging. With no fence and no guards, a wreck near people becomes a parts yard. In a remote, resource-constrained area, aluminum, steel brackets, copper wiring, and hydraulic line are too valuable to leave untouched. Over the years, anything reachable and unboltable was stripped away. The 2003 survey documented the exact toll of this continuous attrition. The most critical structural loss involved the undercarriage system. The starboard landing gear was completely missing from the aircraft. The entire mechanical leg, including the massive trunnion mount, the heavy oleo shock strut, and the wheel assembly, had been severed and hauled away. The absence of this primary load-bearing pillar fundamentally altered the stability of the wreck. The landing gear on a torpedo bomber is engineered to absorb massive dynamic drop loads, supporting the tremendous weight of the fuselage and ordnance. Without the starboard gear supporting the right side, the heavy center section of the aircraft settled directly onto the uneven dirt. This physical collapse induced a constant, uneven torsional load across the main wing spar, stressing the aging aluminum far beyond its intended static limits. Furthermore, the exposed spar attach points, now resting directly in the damp soil, became highly vulnerable to rapid moisture penetration. The attrition extended far beyond the landing gear. The entire left outer wing assembly had been stripped away from the central wing root. The separation point showed clear signs of manual dismantling rather than kinetic tearing from an impact sequence. The loss of the left wing drastically unbalanced the surviving airframe. Removing the left wing structure shifted the center of gravity severely to the right. The remaining right wing, still firmly attached to the fuselage, acted as a massive lever arm. Every time tropical storm winds moved through the exposed airstrip area, the asymmetrical aerodynamic profile caught the gusts. This transferred repeated rotational stress directly into the fragile center wing box, further weakening the structural continuity of the bomber hull. The removal of the outer wing also exposed the internal wing box cavities, fuel tank bays, and complex control cable routing to daily rainfall, accelerating the chemical degradation deep inside the airframe. Despite the severe loss of modular systems, the core shell remained intact enough to establish absolute proof of identity. The primary fuselage stringers, the empennage, and the complete right wing retained their original factory configuration. The assessment team successfully verified the specific technical markers and rivet patterns of the Nakajima B5N2 design. The remaining metal skin, though heavily oxidized and brittle, still held the structural continuity required to classify the wreck as a verifiable historical artifact rather than a scattered, unidentifiable debris field. The core shell was conclusively identified, marking a critical partial success for the forensic survey. However, verifying the identity of the aircraft immediately introduced a severe handling constraint. The surviving structure was no longer a rigid, mechanically sound vehicle. It was an unbalanced, fragile shell resting unevenly on jungle soil. The thin aluminum skin was deeply pitted from moisture exposure, and the internal ribbing was highly susceptible to buckling if lifted from the wrong stress points. The geographical isolation of the airstrip meant that heavy cranes and specialized aviation transport cradles could not be deployed directly to the site. The recovery team had to formulate an extraction plan relying strictly on limited manual labor and standard logistics equipment. The aircraft needed to be moved thousands of miles across the ocean, but the unbraced structure could barely support its own collapsed weight on the ground. How do you transport a compromised, wide-span bomber hull out of a remote jungle without inflicting further structural damage? In 2003, the recovery team faced a rigid spatial boundary. Moving a wide-span aircraft out of a remote jungle required breaking down an aging airframe to fit inside standard maritime shipping boxes. Reportedly, salvagers Ian Whitney and Bruno Carnevale arrived at the site to execute this specific extraction. Their immediate operational objective was not restoration, but physical stabilization and transport logistics. The airframe could not be lifted intact by a heavy transport helicopter, nor could it be towed safely over the primitive regional dirt roads. The only viable path to preservation was commercial ocean freight. Ocean freight meant one thing: the aircraft had to come apart at its factory joints until it fit inside standard containers. Container limits now dictated every move. Whitney and Carnival had to break the bomber down into tight, modular sections, then pack them like freight. A standard shipping box offers roughly 7 feet and 8 inches of internal width, while the surviving right wing spanned well over 20 feet, and the main fuselage structure measured over 30 feet from the firewall back to the tail cone. To meet this rigid geometry limit, the team initiated a controlled disassembly of the hull. They were explicitly forbidden from taking the expedient route of cutting through the aluminum skin with high-speed power saws. Slicing the airframe would permanently destroy the historical and structural continuity of the rare machine. Instead, the salvagers had to locate, access, and separate the exact factory joining locations engineered by the original manufacturer. This operation required clearing decades of compacted soil, biological growth, and trapped moisture from the interior fuselage bays just to reach the primary structural bulkheads. The earlier effects of scavenger attrition meant the left wing was already detached, which simplified the clearance on one side, but the remaining right wing and tail section demanded intense manual labor. The team systematically targeted the heavy steel attachment bolts connecting the main wing spar to the center section. Because the aircraft had suffered from over half a century of jungle exposure, these steel fasteners were heavily oxidized and locked within their aluminum housings. The salvagers applied penetrating chemical solvents and precise manual torque to break the oxidized bonds. They had to extract the bolts slowly to avoid shattering the surrounding, highly brittle aluminum spar webs. Once the mechanical connections were severed, the recovery crew carefully detached the massive right-wing assembly. They then moved to the rear of the aircraft and separated the empennage from the aft fuselage frame. Separating the primary aerodynamic surfaces from the fuselage introduced a new handling hazard. A hollow aircraft hull relies on its attached wings and tail for lateral rigidity. Without these structural components, the heavily corroded central cylinder became highly susceptible to buckling under its own static weight. Whitney and Carnival had to construct custom wooden support cradles to brace the bare fuselage. Loading the separated sections into the shipping containers required extreme precision. The team slid the fuselage inside the steel box, carefully guiding the fragile aluminum skin past the narrow container doors. Clearances were measured in mere inches. They secured the fuselage to the wooden floor using heavy-duty cargo straps, ensuring the downward tension was distributed across the strongest remaining internal bulkheads. The detached right wing and the tail section were subsequently loaded and strapped into secondary cradles. This completely immobilized the irregular shapes against the dynamic pitching and rolling forces inherent to ocean transport. By the end of the operation, the entire remaining footprint of the historic bomber had been successfully compacted into standard freight dimensions. The containerized transport geometry was fully achieved, transforming a vulnerable jungle wreck into a secured cargo shipment. The heavy steel doors closed, locking the aluminum components away from the tropical humidity for the first time in nearly 6 decades. Whitney and Carnival achieved a complete success for the physical extraction phase. The sealed boxes were loaded onto transport trucks and moved away from the airstrip boundary, heading toward the coast. The logistical hurdle of jungle extraction was cleared, but international commercial shipping introduces entirely different operational boundaries. Can an extracted warbird clear sovereign port authorities without facing a hard legal freeze? The legal boundary closed at the port of Leh. The physical extraction from the jungle was complete, but moving a historic military artifact across international borders triggers sovereign control. The shipping containers holding the disassembled bomber reached Leh for export preparations, then the movement stopped. Reportedly, the container was impounded amid an export and ownership dispute involving Papua New Guinea authorities and the National Museum. The sealed boxes sat on the dockside while the case worked its way through local legal and administrative channels. The dispute was said to have been settled in a local court case in 2005, and the container was finally cleared to depart in late 2005 or early 2006. With the impoundment defeated, commercial freighters carried the disassembled aircraft out of the tropical zone. The shipment traveled to a specialized restoration facility in New Zealand known as Pioneer Aero. When the engineers finally unsealed the shipping doors, and they relied on the established containerized transport geometry to carefully slide the fragile hull sections out of their protective cradles. Moving the airframe into a climate-controlled hangar marked a permanent shift in its preservation baseline. The ambient humidity was mechanically stripped from the air, instantly halting the broad surface decay that had plagued the machine since its abandonment. However, the legacy of that decay remained deeply embedded inside the surviving mechanical systems. As the Pioneer Aero team conducted their baseline structural survey, they encountered severe operational lockup across the airframe. The most critical failure point was the port landing gear assembly, which was completely immobilized. The engineers identified a massive galvanic freeze, locking the heavy shock strut in place. Years of moisture pooling in tight mechanical housings causes dissimilar metals to fuse together through oxidation, requiring specialized chemical release or machining to break the bond without shattering the part. The mechanism is brutally simple. Rust expands. As the heavy steel landing gear shaft rusted inside the aluminum trunnion, the expanding iron oxide crystals filled the microscopic clearance tolerances of the original factory assembly. This volumetric expansion exerted immense outward pressure, effectively welding the port strut directly into the wing root mounting bracket. The gear could not be retracted, extended, or safely removed. Applying standard wrench torque or heavy blunt force was entirely forbidden. High stress loads would instantly crack the brittle, irreplaceable aluminum housing, permanently destroying the load-bearing integrity of the left side. To free the seized shaft, the restoration team had to use slow, non-destructive methods, extended chemical soaking, and careful mechanical work until the corrosion bond finally gave way and the port gear strut released from its housing. Releasing the port undercarriage solved one localized constraint, but the team faced a massive structural void directly adjacent to it. The entire left outer wing was absent from the inventory. Without this major aerodynamic surface, the aircraft could never bear its static weight evenly or achieve structural completion for a museum exhibition. The original manufacturer had been dissolved decades prior, and the original engineering drawings were lost to history. How do engineers replace a missing wing when no factory blueprints survive? With no factory blueprints to consult, the team had to treat the missing wing as a reverse engineering problem. Fabricating a load-bearing aerodynamic structure still demanded precise measurements of spar webs, rib spacing, and attachment geometry. The engineers had to generate dependable specifications from the surviving right wing and other reference materials, not from factory plans. To bypass this lack of documentation, the team turned to mirror fabrication. With an intact right wing as a reference, they used high-resolution digital scanning to capture the wing's external curvature and key fastener locations. That data was imported into computer-aided design tools and mirrored across the aircraft's centerline to produce a highly accurate digital pattern for the missing left side. With the mirrored model in hand, specialized metalworkers began cutting, forming, and riveting fresh aviation-grade aluminum. They systematically manufactured a full-scale reproduction of the missing left wing. The fabricators rigorously matched the exact structural dimples, internal bracing spans, and material gauge thicknesses dictated by the scanned 1940s original. Because the core fuselage had retained its baseline kinetic neutrality from the original wheel-down landing, the mounting brackets on the center wing box remained perfectly aligned and geometrically straight. This unbroken factory alignment allowed the newly manufactured left wing assembly to mate seamlessly with the original spar attach points. Furthermore, the mechanics had fully resolved the severe galvanic freeze that previously locked the flight control mechanisms inside the cockpit. This clearance ensured the newly routed aileron cables passing through the reproduction wing integrated perfectly with the restored control stick. With the structural geometry stabilized and the airframe reassembled, the aircraft transitioned out of the engineering shop and into its exhibition phase. In the early 2010s, the museum in Hawaii, then known as the Pacific Aviation Museum Pearl Harbor, now the Pearl Harbor Aviation Museum, acquired the recovered sections. On April 18, 2016, the museum publicly unveiled the wing and a portion of the fuselage for the first time. Over the following years, ongoing conservation work, reproduction wing fabrication, landing gear repairs, and skin stabilization rebuilt the aircraft's silhouette for display. The end state of Tail 302 also shows what decades-long salvage can do to a single machine. Major subcomponents can end up preserved by different hands. While the recovered airframe sections are now conserved under climate control and displayed in Hawaii, the aircraft's engine was removed years earlier and is reported to be preserved and displayed in Kokopo, Papua New Guinea. Even split across the Pacific, the recovery still achieved its core aim, pulling a highly vulnerable jungle wreck through legal boundaries and into conservation, then rebuilding missing geometry through digital reverse engineering. Tail 302 remains an irreplaceable forensic artifact of naval aviation history and is widely regarded as the most complete of only two substantially preserved B5N Kate survivors.